Hi everyone, my name is Ofe Desmond, and my presentation is about face aging with conditional generative adversarial networks. So this is going to be the outline of the presentation. I'm going to start with the introduction to face aging, and I'll talk about the introduction to generative adversarial networks, which are GANs. Then the objective of the study of the paper. Then I'll give a brief overview about c-GANS and how they work, and then I'll move on to how how the writer went about doing the training of the c-GANs, and how the results were evaluated. And then from there, we end with the conclusions and summary of the paper. So, face aging, another name for face aging is called age synthesis. So face aging basically refers to when we aesthetically rendering a face image with natural aging and rejuvenating effects on the individual face. There are various applications of face aging. Some of them are in we use it for cross-age face recognition. We also use it for finding lost children, just in case a child got lost. Someone got lost during their childhood. 20 years later as well, we can be able to determine how the person's face will be looking like in 20 years and help find that child. We also use it in the entertainment sector as well. So the traditional face aging approaches can be categorized in two main categories, which are the prototyping ones and the modeling ones. So the prototyping approach basically estimates the average faces within predefined age groups, whether during the youth or people who are in the mid 30s or old, examples like that. But then the issue with this is that they totally discard the personalized information, which sometimes results in unrealistic images, which may not even be related to the person at all. Now, for the modeling approach, this one uses parametric models to simulate the aging mechanisms of muscles, skin, and skull of a particular individual. Now, as discussed earlier on, the limitations of these approaches is that they miss the global comprehension of a human face. That's basically a person's traits, such as facial expression, possible facial accessories, for instance, like beard. They easily miss out on this. Now, this paper, the objectives of this paper are into can be divided into two main categories. So the first objective was to design an c-GAN, c-GAN and the conditional generative adversarial network to generate high quality synthetic image within required age categories. So for instance, we generate the image for maybe how the person will look like when it's between 20 to 30 years, between 30 to 40 years, 50 to 60 years, examples like that. Also, the other objective was we propose a novel latent vector optimization approach was proposed, which allows c-GAN to reconstruct the input face image whilst preserving the original person's identity, which is very key to what the writer wanted to achieve. So let's start with an introduction to GANs. So we know a GAN image generation can be achieved using GANs, as we discussed in class. So GANs are explicitly trained to generate the most plausible and realistic image, which are hard to distinguish from the real data. So this is a layout of a GAN, basic layout of a GAN. So GAN is basically a pair of neural networks, the generator and the discriminator, as you can see there. Where the generator's goal is try to generate fake images, while the discriminator's goal is to distinguish real face images coming from the image, coming from being generated by the generator, and the system and the discriminator's goal is trying to distinguish between real face images coming from the image distribution, real image distribution, and then synthetic images produced by the generator. So the generator tries to fool the discriminator, and the discriminator tries to find a way to stop that. So both networks are iteratively optimized against each other in what we call a minimax game, hence the name adversarial, as the weights are updated iteratively over time. So let's look at GANs in action. So we can see from here, let's say, so GANs learn a loss function. So from here we see the training goal for the generator is to maximize. So this is the input in the first section of our screen here, and this is being put in the generator. So the training goal for the generator is to maximize the probability of the discriminator making a mistake by creating fake images. Now the discriminator also already has a set of real images which it compares the images being generated against the generator against. So the training goal for the discriminator is to maximize the probability of identifying real versus fake images correctly. So GANs learn a loss function that tries to classify if the output image from the generator is real or fake, while simultaneously training a generative model to minimize the loss function. So basically the generator wants to minimize loss and the discriminator wants to maximize loss. That's the whole way of the training is going to happen. Okay, so GANs have been used. People have tried to use GANs for face aging. So some of the shortcomings of previous GAN-based methods of face modification as follows. So a common problem of previous GAN-based methods for face modification is that the fact that the person's original identity is often lost in the modified image. Sometimes the face aging images will be created, and you realize that there's nothing even in there that looks like the original person's identity. Therefore, in this study, the writers try to focus mainly on preserving identity, focus on identity preserving face aging. That's trying to make sure the individual's identity is still in there while the face aging is applied. So now let's look at c-GANs, how c-GANs work, what the c-GANs work. So c-GANs basically extends the concept of GANs. So from our previous picture which we saw here, we can see the input is just the input there, which is just a random noise. Okay, but then we go to the c-GAN. Now we see instead of just having a latent vector there as the input, now as part of the input, conditions are also being added in here now. So this is basically how the c-GAN differs from the GAN. So the c-GAN model allows the generation of images with certain attributes, with certain conditions. So now certain conditions are added to the input values. So the c-GAN is then trained so that both the generator and discriminator models are conditioned on class of labels. So we condition it on a class of labels. For instance, you could use the age groups as a condition here. Now the condition is performed by feeding a class label or the condition into both the discriminator and the generator input layers. So that's how this is done. As you can see over here, the class label or the conditions, in addition to the random noise, are being fed into the input layer of the generator and both the discriminator. So that's just the difference between the c-GAN and the GAN. So to try to get this into perspective, so looking at the loss functions for GANs versus c-GANs, I think this will point out exactly what I was talking. So GANs and c-GANs, they learn through a loss function that tries to classify if the output image is real or fake, while simultaneously training a generative model to minimize the loss function, as we said earlier on. Now we can see from the loss function of the c-GAN that the generator and the discriminator models are conditioned on a class label. So if you look closely for the c-GAN, that is being conditioned on y, which is a class label. You can see that. But then for the GAN case, we can see there's no, it's not being conditioned, while it is not the case for GANs. So that's where the main difference is. Whilst the loss function for the generator discrimination for c-GAN is conditional on a class label, as we can see on the second in the second equation. That of GAN is not. So that's where the main difference is. So the first aging method which was used in this method is based on GAN. The first aging method being employed by our users is c-GAN, and then the c-GAN is trained as following. Given the input of face images, so as we see in the first there, I can point the screen, but hopefully you are all able to follow. Given an input of face image x of age y, we try to find an optimal latent vector z, which allows us to generate a reconstructed face, as you can see there, which allows us to generate a reconstructed face as close as possible to the initial one. So that's what's happening in the first step there. Then in the step 2, after we do that, then given the target age y target, we now generate the resulting face image by simply switching the age at the input of the generator. So that's how we go about, the c-GAN goes about its training, and that is a loss function it's used in training the c-GAN as well. So we talk a little further about the c-GAN training. We can see the c-GAN model proposed uses the same design for the generator G and the discriminator D as in GANs, as I described about. It's just something similar. Now the writers injected, so we talk about an c-GAN having, the only difference between an c-GANs and GANs is that the input conditions are added to the input as well. So in this case of our writers, they also injected the conditional information at the input of G and at the first convolution layer of D as well for this work. Now the conditions they inputted were 6 age categories. So they used 0 to 18, ages 0 to 18, or 19 to 29, 30 to 39, 40 to 49, 50 to 59, and 60 plus years old as their conditions in this case. As part of the training set, the training set contains at least 5,000 samples in each age category. Now, the c-GAN was optimized using the Adam algorithm, and then it was trained with 100 epochs. So the c-GAN was trained on the IMD Wiki clean data set of about 120,000 images in total. So after their training, this is one of the results we pulled out, a sample result from the training. So this figure we see here illustrates the synthetic faces of different ages generated with our c-GAN. So each row corresponds to a random latent vector z, and 6 columns correspond to 6 age conditions y. So we can see from here that we pick a lady. So when we pick the first lady in the first row, this is how she will look like between 0 to 18 years. This is 19 to 29, how she will look like. How she will look like between the ages 30 to 39. How she will look like between 40 to 49, 50 to 59, and 60 plus. So the same for the young man. The man below in the second row is the same thing. We look at how he's going to look like over the years. So in this, it's clear for us to observe that that we are able to, these results are able to encode the person's identity, or facial expression, facial pose, or the hairstyle. We can all see all this being shown in there, and then the person's identity, we can see it's obvious, it hasn't been lost in there, which was very key to what our writers wanted to do, and we can see the results really show that. So how did they evaluate this their c-GAN based on the results? How did they evaluate to see that, oh, this really worked? So to evaluate their results, they use the state of the 8 art age estimation CNN to do that. So CNN is convolutional neural network. I'm sure everyone knows about CNN in our class by now. The professor has went over this several times. So now the age estimation CNN on real images from the test part of IMD Wiki versus 10,000 synthetic images generated by c-GANS. So these two were compared. Now the resulting mean age estimation accuracy on synthetic ages was just about 70% lower than the natural ones. So the resulting mean age they got was just about 70% lower than the natural ones if they are used the real images. So this went ahead to prove that, in fact, the model can be used for generation of realistic face images with the required age. So since the difference is not that much, 70% is sounds a little big, but then this is one of the best results that has been achieved in a while. So then this shows that with some more tweaks here and there, their model can indeed be used for generation of realistic face images with the required age, and hence their project was a success. So let's talk about the conclusions here. So the writers successfully developed a new method for synthetic aging of human faces, which was based on age conditional generative adversarial network. So they wanted to base it on conditions, with their conditions were age categories, how to see how the person ages along, and they were able to achieve this as we showed in here. You could see this has been showed in categories, so that was great. Now also their unique approach of identity preserving using latent vector optimization approach to preserve the original person's identity in the reconstruction was also really a key factor to them, which they managed to achieve. Now, so in basic, the c-GAN had two steps. The first step was that you input a face reconstruction requiring the solution of an optimization problem in order to find an optimal lattice approximation Z star. And then from there, we did face aging. Face age itself was performed by a single change of the conditions Y at the input of the generator. So we talked about the conditions earlier on, which are the age categories. And this can be used to preserve identity not only for face aging but also for other face alterations. For instance, even if the person adds a beard or sunglasses, we can easily be able to easily identify them. So this research paper was really a great project, and it achieved its result, which has helped easily preserve the identity of faces. For me personally, I think I find it very useful. For instance, if a kid gets missing whilst it was even 10 years, 80 years from now, we can still find the kid using the application of c-GANS, which is really great. So that's the end of my presentation. I really thank you. I had some questions over here which will end with those questions. So my first question was, what is the difference between the generative adversarial networks, GANs, and conditional generative adversarial networks, c-GANs? So you can pause a minute and think about it, and then you can go ahead. So the answer is that it's at the loss function here. We see the easiest way I can show you this is from the loss function. We can see that for the loss function of the c-GAN, the generator and the discriminating models are conditioned on the class label or other modalities, which is why, as we can see in the second row. But then the GANs are not conditioned on that, so that is the main difference. Thank you. And then let's look at the last question. So the last question: GANs and c-GANs have the same loss function, true or false? So I sort of gave away the answer to this one there, but then that is false. They do not have the same loss function. Since c-GANs are conditioned on are conditioned on the conditions, but then the other ones are not. So c-GAN is conditioned on those conditions such as age groups and categories, but GANs are not conditioned on any other thing. So that's the end of my presentation. Hope you enjoyed it. Thank you very much for listening. And this is a very great paper. I hope, I encourage all of you to look at it because I really learned some great things from this paper. Thank you all.